Welcome to section 7.4. In this section, we're going to be looking at how to maximize and minimize functions of several variables when there is some sort of constraint or restriction placed upon the functions. So in order to do this, we can't approach it the same way that we did when we were unrestricted. Those we were looking for relative maxes or mins across an entire function. But a lot of times, especially when you're talking in terms of application, we are not free to take any value that a function might give us. We are restricted or limited based off of like real life restrictions, real life kind of limitations, where maybe we don't have enough materials for something, maybe there isn't enough money for something, and so you have to work within the confines of what you have. So we can't use the second derivative test like we saw in the last section. What we can use is called the method of Lagrange multipliers. So the method of Lagrange multipliers says the following: to find the maximum minimum values of f of xy subject to the constraint g of xy equals k, we do the following. Find all values of x, y, and lambda such that fx equals lambda times gx, fy equals lambda times gy, and g of xy equals k. So find all values of x, y, and lambda. Lambda is a Greek letter. It's like a Greek letter L like Lagrange, such that fx equals lambda gx, fy equals lambda gy, and then the constraint, g of xy equals k, where k is some constant. Once we have all these values, we're going to evaluate f at all the points that we got from step A. The largest of these is the max, the smallest is the min. Okay, so evaluate f at all the points from step A. The largest is the max, the smallest is the min. So lambda, that Greek letter L, lambda is what we call the Lagrange multiplier. Okay, so again, L for Lagrange, and it's being multiplied in these equations. What the lambda value actually tells us physically about the problem, it tells us the rate of change of the max or min value with respect to the constraint. So each of these problems are going to look a little bit different, even from each other. When we're taking the partial derivatives, we are sometimes going to be looking for lambda values and trying to use lambda to find x and y. There may be times when we don't even need lambda and we can find x and y all on our own. Every problem is going to be a little bit different. So let's take a look at this example so you can kind of see how this works. So find the extreme values of this function, x squared plus 2y squared. On the circle, x squared plus y squared equals 1. So this function has its own maximum and minimum values somewhere, possibly, but we don't want the max and mins of the entire function. I only am looking at the parts that are touching this circle. Okay, so there's some function out here, and then when I trace the circle around the function, I look and I see where is the highest and where is the lowest that is on the function and on this other formula or the constraint. Okay, so this right here, this is g of xy. How do you know which one is the constraint? Well, the constraint is going to be equal to a number, equal to a constant. So we need to take the partial derivatives. So we get fx is 2x, fy is 4y, gx is 2x, gy is 2y. So we're going to get our two equations. So we'll have fx equals lambda times gx, and fy equals lambda times gy. All right. Now, we need to solve this for x and y points, and then potentially any lambda values that might help us solve for those as well. So I'm going to start with this first one here. Please don't divide by 2x to both sides, because then you're going to lose one of your solutions. So I'll show you what I mean. If we subtract this over, so 2x times lambda minus 2x equals 0, factor out the 2x instead. We get x is 0 or lambda is 1. This presents us with two separate cases. Okay, so x equals 0 is one case, lambda equals 1 is the other. If you had divided away the 2x, you would lose this one entirely, and that could end up proving costly. For the lambda equals 1 case, so we'll take this and put in 1. So we get 4y equals 2y, so 2y equals 0, so y equals 0. Okay, so this value corresponds to lambda equals 1. Now, lambda is not a part of the point. It's just a kind of a medium. It's a means through which we get to the points. So what do we actually use to find the other values? The constraint, the restriction. So let's see here. So when x equals 0, we have 0 squared plus y squared equals 1. So y equals plus or minus 1. Those values will go with the x. And then when lambda equals 1, so y equals 0, x squared plus 0 squared is 1. So x is plus or minus 1. So it turns out we're going to have 4 critical points here. Yeah, and actually we don't even really need to label these as critical points. What we're looking for, so our possible extrema, we have 0, -1, 0, 1, -1, 0, and 1, 0. So, and like I said, I'm not going to really classify them as critical points because we didn't like set the derivatives equal to 0 and go through that whole process. But all we need to do for this one is just find their outputs. So we're going to check outputs. So we're going to do f of 0, -1, f of 0, 1, f of -1, 0, and f of 1, 0. So let's see, we get 0 and 2, 0 and 2, 1 and 0, 1 and 0. The method of Lagrange multipliers says that the highest output is the max, the lowest output is the min. In this case, these points will share those titles because they're both the highest and then the lowest. So we're going to have, so the maxima of f on the circle is going to be 0, -1, 2, and 0, 1, 2. And the minima of f on the circle is -1, 0, 1, and 1, 0, 1. And those are, again, not the maximum and minimum values of the entire function as a whole, but these are the largest and smallest outputs that you'll get on this function, but also on that circle. So that's our restriction. Our constraint was that we had to be on the circle, and then we got the largest and smallest values possible while also obeying that extra rule. For our next example here, we're going to circle back to a formula that we talked about a few sections ago. This is the Cobb-Douglas function that describes the level of production, the production of units of an item based on labor and capital. So the production of a manufacturer is given by this function. So f of xy is 30 times x to the 1/5 times y to the 4/5, where x represents the units of labor in hours, and y represents the number of units of capital in dollars invested. Labor costs 15 per hour, and there are 8 hours in a working day, and 250 working days in a year. So we've got a lot of kind of numbers to go through there in just a minute. The manufacturer has allocated $4.5 million this year for labor and capital. How should the money be allocated to labor and capital to maximize productivity this year? Okay. So now our constraint. So x is the number of units of labor in hours. Y is the number of units of capital in dollars. So for our labor, so we're looking at the restriction, right? Our restriction here is purely financial. So that's going to be, there are only there's only $4.5 million to spend for this company. So they need to allocate it between labor and capital. For the capital, that value is just going to be y. That's just the number of units in dollars. That's how much money. For the labor, it's not as simple as just plus x for the labor. X is the number of hours, but those hours cost $15 per hour, 8 hours a day for 250 working days in a year. So we would take, right, 15 per hour times 8 hours times, or hours per day, times 250 days. And that number ends up working out to 30,000. So we get 30,000 hours per, $30,000 times the number of units of labor. And then plus y is the number of units in capital. Okay. All right. So when we look at the function, the formula up here, we need to take the partial derivatives. So we're going to get fx, and we're going to have to use the power rule here. You have to be very careful with its use here because we do have fractions in those powers. So for this one, we ignore the y, we take the derivative with respect to x. So we bring down the 1/5, and then we have x to the negative 4/5 times y to the 4/5. So because you subtract 1 from the power. So I'm going to move that down, and I'm also going to cancel the 30 with the 5. So we're going to get 6y to the 4/5 over x to the 4/5. And then for fy, times x to the 4/5, 1/5, times, now we bring down the 4/5, and y is to the negative 1/5 now. A little cancellation. We get 4 times 6, so that's 24. 24x to the 1/5 over y to the 1/5. So these are our two formulas for fx and fy. So gx and gy are nice and simple. So we're going to set this equal to lambda times gx is just 30,000. And set this equal to lambda times gy, which is just 1. Now we could try to solve for some relationship in like x and y and lambda and try to solve the equation. It gets a little convoluted. So what we're going to do is we're actually going to solve each of these for lambda. So I'm going to divide the 30k over there, or 30,000. So we get y to the 4/5 over 5,000 x to the 4/5. This one, it's only times 1, so it's actually just the same thing. 24 x to the 1/5 over y to the 1/5. And now here's my purpose in doing that, is now that both of these are equal to lambda, I can set them both equal to each other. Okay, so lambda, we don't even really need to solve for the value of lambda here. A lambda is just acting as a go-between for these two. So we get y to the 4/5 over 5,000 x to the 4/5 equals 24 x to the 1/5 over y to the 1/5. And I know it seems like it won't work out nicely, but y to the 1/5 times y to the 4/5 is just y. X to the 4/5 times x to the 1/5 is just x. So we get y equals 24 times 5,000 is 120,000 x. And this looks much nicer, like we could do something with this. And we can. So we can now take this relationship and use it back here in the constraint. So we'll just sub in for the y right there. So we're going to have 4.5 million equals 30,000 x plus 120,000 x. If we solve that for x, combine and divide, x is 30 and y is 3.6 million. Now, I know that seems like a major discrepancy, but remember that for x, this is 30 units of labor. So we need to convert it into dollars. 30 units of labor. So x equals 30 times 30,000. We get $900,000 in comparison with $3.6 million. It's still a pretty wide margin, but that's at least a little more in the same ballpark. So we get our two values that we need. And it didn't really ask us what the maximum production would be, but if we wanted to find it, I would just tell you that this is 10,413,279. This is certainly work for a calculator. Don't try to do all these numbers in your head. So we can say to maximize production at 10,413,279 units. They should spend $900,000 on labor and $3,600,000 on capital. And remember, the constraint, the restriction, is that it had to add up to $4.5 million. And if you add those two numbers together, they definitely add to 4.5 million. So this is satisfied through that constraint, that condition. So this is the most effective way for them to utilize their money in this situation. But that brings us to the end of section 7.4 and to the end of chapter 7. So congratulations, making it all the way to this point. I will talk with you all very soon about what comes next.